Aspects of the cerebrovascular response to carbon dioxide. One way of evaluating the health of the cerebrovasculature in terms of cerebral vasodilatory reactivity or reserve is to apply a stress test. This test involves presenting a vasodilatory stimulus and observing the effects on cerebral blood flow. The stimulus most often used is carbon dioxide, which provokes a global vasodilation by exerting a relaxation effect on the smooth muscle cells throughout the vasculature. This talk is about how the physiological aspects of the vasodilatory response to CO2 affect the measurement of cerebrovascular health. The pattern of the CO2 stimulus applied can be varied, with step changes providing an examination of the speed of response, and a slower ramp change providing a more detailed look at the pattern of the response as CO2 tension increases. Responses to CO2 of individual extracranial supply vessels, like the carotid artery, as well as the intracranial middle cerebral artery, can be assessed using transcranial Doppler measurements of blood flow velocity. A whole brain voxel-wise assessment commonly uses magnetic resonance imaging of the blood oxygen level dependent signal, the BOLD signal, as an estimation of blood flow changes. This graph is an example of a testing protocol, including both step and ramp changes in the CO2 stimulus, shown in blue, and the resulting whole brain average BOLD response, shown in purple. Note that while the whole brain average BOLD response provides an overall view, the responses of individual voxels can show many different patterns. A commonly used assessing metric is the change in blood flow per change in the partial pressure of arterial CO2 tension, calculated by linear regression. It's called the Cerebrovascular Reactivity, or CVR for short. Voxel-wise maps of CVR can be used to assess vasodilatory ability and cerebrovascular health. Here is an example of the use of CVR maps to assess the progress of changes following bypass surgery. Note the use of cool blue shades to show where the CVR is negative and BOLD decreased as CO2 increased. Warm yellow to red shades indicate a healthy positive CVR where BOLD increased with the CO2. Understanding the basic physiology involved in this scenario is essential for correctly interpreting CVR. The cerebrovasculature is the complex network of blood vessels that distribute blood to the brain. One way of envisioning this network is to consider each vessel as a flow resistance, as shown here. Cortical blood flow is supplied to the circular Willis, COW, via the source arteries, carotid and vertebral, distributed bilaterally to the hemispheres, and then by the major intracranial arteries, the middle cerebral artery, MCA, the anterior cerebral arteries, ACA, and the posterior cerebral arteries, PCA. And these feed their region of the cortex via the Peel network to the brain parenchyma. Here is a portion of the simplified resistance model showing the perfusion pressures of the flow pathway. On the left, one flow pathway, the red line, through the cascade of resistances from the source arteries to the microvasculature. The glow effect indicates a decrease in resistance in order to increase blood flow in response to an increase in local metabolism via neurovascular coupling. In the center, the loss of perfusion pressure, the green line, is shown as blood flows down the resistance cascade. And on the right, the percentage of the total vascular resistance each segment of the pathway offers to blood flow. In this model of a part of the network of cascading vascular resistances, each resistance lowers the downstream perfusion pressure. And this is according to the flow through the vessel resistance as determined by Ohm's law, where pressure loss equals resistance times flow. Note that at resting blood flow, there is a loss of perfusion pressure of about 20 to 30 millimeters of mercury from the mean arterial pressure, MAP, to the main intracranial arteries, due to the resistance of the brain supply arteries. So at each resistance level, a further pressure loss is incurred, so that there is a cascade of pressure loss throughout the entire flow pathway from source arteries to tissue capillaries. For example, with a mean arterial pressure of 100 millimeters of mercury, the pressure at the main intracranial distribution arteries is 60 millimeters of mercury, and downstream of the peel arteries, less than 40 millimeters of mercury. Now consider that this pattern of flow pathway pressure loss occurs over the entire cortical network of vascular distribution to form a spatially complex distribution of pressure gradients, and that this distribution varies with time as the parenchyma reacts to various stimuli. Here I show in A that the resistance model of a single flow pathway from the previous figure can be simplified further by combining all local resistances into one and all resistances upstream into one. In B, nearby local resistances share a common upstream source resistance. It is this model that Faraci and Heisted used to explain the Steele phenomenon, whereby vasodilation may increase flow in a region, but cause a decrease in flow in an adjacent region when they share a common source. Vasodilation as CO2 increases reduces the vascular resistance in a sigmoidal relationship as shown in C, due to the limits of vasodilation and vasoconstriction. Here is a computational model of the Faracian-Heisted demonstration of cerebrovascular Steele. I have an upstream resistance, and I have two branches, branch A and branch B. The upstream resistance is adjustable, and you'll notice that that upstream resistance has caused a pressure loss because of the flow going through it. We started with an input pressure of 100, but now we're down to 50. So we've had a considerable pressure loss. That pressure loss will change with the upstream resistance. And so if I reduce the resistance, the pressure will go up. And if I increase the resistance, the pressure will go down. And you'll notice that the flow, the blue columns here in branch A and branch B, have also the resistance up, pressure down, so flow is down. Resistance down in the upstream resistance, pressure goes up, and flow goes up. So I'll leave that upstream resistance at its setting here. And let's see what's happening if we have response in branch A via neurovascular coupling, perhaps demanding an increase in flow. So we get vasodilation and the resistance goes down. You'll notice that then the flow in branch A, the blue column there, that goes up. It goes up quite nicely. So yes, indeed, that's good. That's what it wants to do. But you'll notice that something else also happened. If we look at the pressure gauge here while I do that, I reduce the resistance, I increase flow in branch A, but the pressure to the two branches, the perfusion pressure, goes down. Now that perfusion pressure going down means that branch B flow will also go down because of that. And indeed it does. And so this is cerebrovascular steal. So branch A reduces its resistance to increase its flow and steals the flow, so to speak, from branch B. But it occurs because the perfusion pressure is altered as I increase the general flow through the upstream resistance. The pressure loss in that resistance is greater, and the perfusion pressure goes down. So what could be done about that? Well, if branch B is healthy and it wants to maintain its flow, we can reduce the resistance there and cope with that. You'll notice that also has an interaction because you're changing the general flow through the upstream resistance, so the perfusion pressure is changing. It's shared by both branches, and so a change in the resistance in branch B also affects the flow in branch A. Branch B flow goes up as I reduce the resistance in branch B, but branch A flow goes down. And that's because the general perfusion pressure has gone down because of the increased flow through the upstream resistance. Now, what can we do about that? Let's go back to normal. And we've seen how if branch B is healthy, it might be able to cope with the fact that branch A is vasodilated and decreased its resistance and increased its flow. Let's do that again. Here we are, and it has stolen the flow here, but that's because the pressure has gone down. But this vasodilatory signal may spread upwards towards the upstream resistance and cause it to decrease, and if it does decrease enough to restore the pressure to what it was, then the flow in branch B is where it should be without having to change its resistance. But the flow in branch A now is too high, which means that we didn't have to reduce the resistance as much. Both of these interactions are going to occur in the cerebrovasculature. But I point out to you that when the CO2 stimulus is applied, it's a global stimulus, and therefore we've already reduced the upstream resistance. And so what amounts to the competition here will reveal steal if branch B is unhealthy and cannot vasodilate when branch A vasodilates. Here are visual models of the mechanisms involved in vasodilation. The upper diagram shows local vasodilation in response to increased neural activity, the neurovascular response, and it's spread retrogradely via the endothelium gap junctions. The lower diagram expands the view from capillary to artery, showing not only the retrograde vasodilation, but also the possible anterograde vasodilation from globally administered stimuli like CO2. Global vasodilatory effects require a quite different understanding of the changes in blood flows and pressures in the cerebrovascular compared to local changes. When arterial CO2 tension is increased, all vascular smooth muscle throughout the cerebral vasculature relaxes. Vessel diameters increase, decreasing resistances, and global blood flow increases. This general increase in tissue blood flow distributed throughout the brain is supplied via the upstream network of resistances. These include the extracranial supply arteries resistances, which change little with CO2. Consequently, perfusion pressure losses occur throughout this complex vascular network, and they increase as CO2 tension rises. One can imagine what a voxel-wise map of the distribution of local perfusion pressures might look like under these circumstances. Such maps would vary with the CO2 stimulus, with a response time characterized by a time constant of redistribution. Consequently, the response time for changes in flow in a voxel are due to 1. The response time of the global spatial distribution of perfusion pressures, and 2. The response time of the local vascular smooth muscle. Finally, note that eventual compensation for this pressure loss due to global vasodilation is provided by an increase in arterial blood pressure, which begins to occur above a threshold CO2 tension of about 45 to 50 millimeters of mercury, as Baptiste Charbonnet and colleagues discovered in 2011. With the previous concepts in mind, consider the measurement of cerebrovascular reactivity, CVR. CVR is the ratio of the change in BOLD to the change in CO2 tension. BOLD is taken as an estimate of cerebral vasodilation and therefore blood flow. As previously discussed, a globally applied CO2 stimulus results in a redistribution of blood flow that will vary not only due to the vasodilatory characteristics of individual vessels, but also due to the global redistribution of perfusion pressure. Consequently, BOLD responses are not instantaneous but slowed to some degree, and BOLD responses may be nonlinear due to the effects of steel. To illustrate the concepts involved in the interpretation of the BOLD responses to CO2, a simplistic approach is taken, initially neglecting possible nonlinearities due to the effects of steel. The time course of BOLD responses is assumed to be exponential, characterized by a time constant. The symbol is Greek letter tau. The following examples are first concerned with the effects of the response time constant tau on the observed BOLD response and therefore the CVR measurement. These examples delineate the transient periods where the vasodilatory response and CVR measurement is obscured by the inability of vasodilation to keep pace with the stimulus change. The first example uses a step or square wave CO2 stimulus. Two voxels have responses with the same steady state CVR, but different time constants. The red voxel BOLD response has no tau effects and follows the CO2 stimulus closely. The green voxel BOLD response is slow. It has a high tau. and can be separated into transient, the yellow dots, and steady state, the green dots, components. To measure the steady state bold CVR of the red voxel, all red points can be used. The slope of the regression red line is the steady state CVR. To measure the steady state bold CVR of the green voxel, only the green steady state points are used. And the slope of the fitted green line is the steady state CVR. If the transient points, the yellow points, are included in the line fit, then the CVR, the yellow line, is reduced, as you can see, and that reflects the effects of tau. These graphs show the effect of transients on the measurement of CVR using a step stimulus. Graph A shows the time course of bold responses of voxels with the same steady-state CVR but with various tau, the colored lines. The CO2 stimulus is a 10 millimeter of mercury step change from a resting value of 40 millimeters of mercury to 50 millimeters of mercury, shown as a dark blue line in graph A. The response graphs B, C, and D plot the fitted regression lines of bold versus CO2 responses and demonstrate that the CVR differs depending on the portion of the time graph chosen to fit. Graph B uses the complete time course from 0 to 250 seconds. Graph C uses points from the initial rest portion and the step portion from 0 to 150 seconds altogether. Graph D uses points from the step portion alone, from 60 to 150 seconds. As can be seen, the effect of transients due to slowed responses on CVR measurement varies with the magnitude of the time constant tau. Calculation of CVR can also be affected by the time range chosen for analysis of these responses. While the CVR measures of the step portion with or without the resting values, graphs C and D, are the same, including the transients of the return to resting after the step reduces the CVR. That's graph B. With noisy data, line fitting is improved by including the resting part with the step, graph C. Using a step CO2 stimulus to measure CVR is simple, but only includes two CO2 tensions in the regression. To discern any nonlinear patterns of the bold response to CO2, the response must be measured over a range of CO2 tensions. Using a ramp, PCO2 stimulus accomplishes this discrimination. The CO2 stimulus shown here in the top graph, blue line, has a resting portion, a ramp, and a portion at an elevated CO2. The upper graph shows the bold responses of two voxels with the same steady-state CVR. The red voxel bold response with no tau effects follows the CO2 stimulus. The other voxel bold response is slow and can be separated into the transient, the yellow points, the ramp, the green points, and the steady-state purple points components. To measure the response of the first voxel, all red points can be used for regression, and the pattern is a straight red line. To measure the ramp response of the second voxel, the transient points, yellow points, are excluded, and only the green points are used. The regression pattern is a straight green line. Nevertheless, the purple steady-state points at rest and at the top of the ramp provide a two-point measure of the steady-state response, the purple line. In summary, the red, purple, and green lines all have the same regression slope CVR, but only the red and the green fits will show any nonlinearities, as will be demonstrated later. Note that one advantage of this pattern of CO2 stimulus is that including all points of the bold response in the regression fit provides a correct CVR measurement, because the effects of transients at the start and end of the ramp on CVR measurement tend to cancel. These graphs show the effect of transients on the measurement of CVR using a ramp stimulus. Graph A shows the time course of bold responses of voxels with the same steady-state CVR, but with various time constants, tau, the colored lines. The CO2 stimulus is a 15 millimeter mercury ramp change in PCO2 from a resting value of 40 millimeters of mercury to 55 millimeters of mercury, shown as a dark blue line. And the response graphs B, C, D, and E plot the fitted regression lines of bold versus CO2 response and demonstrate that the CVR differs depending on the portion of the time graph chosen to fit. Graph B uses the complete time course from 0 to 400 seconds. Graph C uses points from the initial rest portion, the ramp portion, and the plateau portion from 0 to 300 seconds. Graph D uses points from the ramp portion and the plateau from 60 to 300 seconds. And graph E uses points from the ramp only from 60 to 210 seconds. As can be seen, the effects of transients due to slowed responses on the CVR measurement varies with the magnitude of the time constant tau. And the calculation of CVR is also affected by the time range chosen for regression analysis of these responses. In these examples, the CVR ranking from lowest to highest is graphs B, E, C, and D, so that the ramp plus plateau portion of the data yields the best estimate of the CVR and, as graph D shows, is least affected by transients despite their inclusion. One further consideration for the ramp CO2 stimulus is the choice of its rate of change. And these graphs show the bold response to a CO2 ramp of 15 millimeters of mercury, from 40 millimeters of mercury to 55 millimeters of mercury, for ramp times of 1, 2, 3, and 4 minutes. As illustrated, if the ramp rises too quickly, the 60-second ramp, for example, then some slow responses do not catch up to the PCO2 ramp change even before the ramp is finished. Increasing the ramp time can overcome this problem, but extending the ramp time risks introducing bold signal drift. So far, these simulations have dealt with the effect of slowed responses and their transient effects on the bold response to CO2 stimulus and measurement of CVR. A linear bold CVR response was assumed for simplicity. But, as we have discussed at the beginning of this talk, interactions between regions can produce not only nonlinear bold responses, but also negative bold responses, or steal. To explain the origin of nonlinear responses from such interactions, the Farachian-Heisted model is extended, as outlined in A, with branch resistances that vary sigmoidally with CO2, as shown in B. As before, mean arterial pressure, MAP, produces a flow through the supply arteries with resistance R-art to two branches with voxel and reference resistances. There will be a resulting pressure loss through R-art to determine P branch, depending on the total supply flow and competition for flow between the two branches. Here is the simulation of the resistance model as executed by a computer program. The resistance model itself is shown in this panel. There is a control panel here to set the PCO2 stimulus, the resistance sigmoid parameters, and the voxel, and other aspects of the model, as well as the CVR calculation. The resistance sigmoids and their resulting flows versus PCO2 are shown in this panel. And here is a panel showing the time course of the bold response to a CO2 stimulus for several time constants tau. Finally, there is a panel showing the linear regression fits of bold versus CO2 to measure CVR as the slope. So in this model, the sigmoid parameters of the reference resistance are fixed as it represents the competition of an average normal region. The sigmoid parameters of the voxel resistance are chosen to observe the effect on the bold response and the CVR. Indeed, many different bold responses and CVR fits result. For completion, the effects of slow responses with differing tau are also included in the time course simulation and the CVR calculation. Overall, the patterns of bold or flow response observed can be divided into 4 types and were originally described by Fisher and colleagues in 2017 in their publication. Let's use the model to see how changes in the voxel resistance sigmoid parameters produce these patterns. First, the type A response. Here, the examined voxel sigmoid parameters at this moment are the same as the reference resistance, and they overlap. By reducing the voxel resistance sigmoid amplitude slightly, instead of 0.12 to 0.11, we can see now the reference resistance as the black line here, and the voxel resistance as the red line here, over the range of PCO2 from 20 to 60 millimeters of mercury. The resulting branch flows, or bold, versus CO2 are also shown. The blue line for the reference branch and the purple line for the voxel branch. This is the one that we'll be very interested in. The PCO2 stimulus applied is shown in the time graph as the dark blue line. It starts at a 40 millimeters of mercury for a rest period of 60 seconds, followed by a ramp rise of 15 millimeters of mercury over 150 seconds to a plateau of 55 millimeters of mercury held for 90 seconds, and finally back to 40 millimeters of mercury for 100 seconds. And the bold responses with various time constants are shown by the colored lines. The bold versus PCO2 measurements for CVR use the data from 0 to 300 seconds, which includes the initial rest period, the ramp, and the plateau. And a single regression line slope measures the CVR in this final panel for the various time constants of response. As you can see in this case, the the tau transients have very little effect on the regression slope, the CVR, because the effects of the initial and final transients here, the time course, tend to cancel with this particular CO2 stimulus pattern. And that is a type A response. Now for the type C response. Let's continue to reduce the voxel resistance sigmoid amplitude. At 0.05, the bold response is still positive, as seen in the bold versus CO2 panel here. Still positive here. And the time course shows a type A positive response, with the regression fits also showing a positive CVR. Now reduce the amplitude to 0.02. The bold versus PCO2 panel shows a steal response for this very low resistance response. This is repeated in the time course panel here, and the regression line slopes, the CVR, are negative. So this is a type C, or a steal response. In between these two extremes, the bold response patterns are nonlinear, as we shall see. Let's return the voxel resistance sigmoid amplitude to 0.05. And we see a type A response. Now let's move the voxel resistance sigmoid midpoint to a lower PCO2 of 35 millimeters of mercury. The bold versus PCO2 response, the purple line, is now nonlinear, and the time course here shows an initial positive response, which becomes negative as steal occurs in the hypercapnic range. In this case, a single line fit for the CVR measurement is affected by the time constant of the response. Fitting a single regression line to calculate CVR does not capture the existence of the nonlinearity. However, a fit of two lines with an inflection point PCO2 is used to show the type pattern. And this is a type B response pattern. A further reduction in the amplitude to 0.02 turns the response into a steal or negative response. And CVR can now be determined from a single regression line slope. However, we're at a midpoint of 35. If we go back to 40, it's very similar. But if we increase to 45, we now see that the bold response to PCO2 is nonlinear. The time course shows an initial negative or steal response, which becomes positive as the steal is overcome in the hypercapnic range. In this case, too, a single line fit for determining CVR is affected by the time constant of the responses and does not capture the existence of the nonlinearity. A fit of two lines with an inflection point PCO2 can be used, and this shows a type D response. Now, with all four resistance sigmoid parameters as variables, it is easy to understand that a multitude of bold responses to PCO2 are generated. Final words. A consideration of the anatomical and physiological aspects of the cerebrovascular response to a global CO2 stimulus provides an understanding of how they affect the assessment of cerebrovascular health using measurements of cerebrovascular reactivity. They show that the cerebrovascular response to a global CO2 stimulus is affected not only by the transient effects produced by slow responses, but also by the interactions between regions that alter the distribution of blood flow. Consequently, the measurement of CVR is influenced. A single regression line slope fails to capture the existence of nonlinearities and so may not always be appropriate.